All right, I'll be talking about the Kerr solution to the Einstein field equations. Feel free, of course, to bug me with any questions that you have along the way. As this is a kind of directly analogous to the Schwarzschild solution, just with one additional important parameter, I wanted to take a less mathematically rigorous approach and do some of the good interpretation of the project. So Schwarzschild solution, just a quick review. I'm using the minus plus 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 signature. Has a g mu nu that is given as we've seen in class with the usual diagonal GTT, GRR, G theta theta, and G phi phi components. And the Schwarzschild radius, of course, is given as 2gm, for m being the mass of the black hole. And I'm using c equals 1 units throughout this. This was found in 1916, which was very early on, and really quite remarkable how simple it is in comparison to the next analytical model which was found, which was and is the Kerr solution. The Kerr solution requires a new coordinate system where you have an additional parameter alpha called the Kerr parameter. And that alpha is equal, you can see here at the bottom, it's equal to the ratio of the angular momentum of the black hole to its mass. You would think perhaps it can actually obtain any value. It is actually a limited parameter bounded between 0 and 1, as we'll see in just a second. But what you can also see is it reduces nicely just to the Schwarzschild solution if you set that parameter alpha to 0. One of the things that I forgot to mention from the first slide, you probably saw it, there's a symmetry. Let me actually just go back. A symmetry in the spherical case with no rotation. And Birkhoff's theorem says that the external solution, in other words, outside of the Schwarzschild radius, that the solution must be given by the Schwarzschild metric in the vacuum. However, in this case, where you do have rotation of the black hole, you break that spherical symmetry, and you no longer has the Schwarzschild solution being appropriate, at least in the fast rotator sense. The Kerr solution, the metric is given here. You'll notice that this is just one form. There are many forms. The Boyer-Lindquist coordinates are very useful, but they were actually not the first ones that were developed. These were this solution was developed a little later on, and the reason why it is preferred when dealing with this most of the time is because it only has an off-diagonal element there and there, whereas other coordinate systems tend to be much more difficult to deal with, and the line element is messy, to say the least. The delta and the sigma are given here are just for convenience, and I've included this just because it is a natural extension if you would like to, where instead of considering not only just the rotation of the black hole but also its charge, black holes can have charge, angular momentum, and mass, and the charge there can be included for Q, the total net charge of the black hole, which usually is assumed to be 0, but it does not have to be. For this, we're going to set this equal to 0. If you did not want to set that equal to 0, then it just expands into, instead of just the Kerr solution, but the Kerr-Newman solution, and changes things a little bit, but isn't that far off from the method presented here. If you would like, by the way, to go through this method on your own, I highly recommend Hartl's book, The Gravity and Introduction to Einstein's General Relativity. Very good for being able to get especially a qualitative feel as to what's going on. And then there's also an archive paper if you would like to go over more of the heavy math and especially the coordinate transformations. It's a very good paper, and you will regret probably reading it if you're doing it for fun. So one of the characteristics which is apparent not only in Schwarzschild but in this one is that it must be asymptotically flat. So in other words, in the limit of r being much greater than gm and the Kerr parameter together, then the line element ds here, if you just take the leading term of each of these components, you will get it reducing to the flat metric, which is what you would assume. There are two additional things which weren't talked about in class, but you might have heard of them before. Killing vectors, they're called, after a guy whose last name was Killing. And they are vector fields in which the metric is preserved. So if you were to translate it along one way, the metric would be unchanged. There's a little explanation down if you'd like to read it, but the Killing vectors are associated with a time component and an angular rotation component, the phi component. And they have conserved quantities that go along with them. For the u here being the 4 velocity, you have a conserved energy, E, and angular momentum, L, per unit mass. We'll get back to that in just a second. If you look back, let me scroll back here. If you look at these terms, the metric, you've got a 1 over delta, and you've got a 1 over sigma. And those are possibilities for singularities, either coordinate or curvature singularities in the in the metric. You can see that from the sigma equation, you get a singularity if r is equal to 0 and theta equals pi over 2. In other words, if you're in the plane of rotation, the equatorial plane. And then for the delta equation, you get a plus or minus term, an inner and an outer horizon, they will be called, where you have the Schwarzschild solution and, of course, the rotation parameter alpha that are included. Going over this just briefly, I didn't want to bring in many of the different coordinate systems because there are quite a few, but one of the coordinate systems called Eddington-Finkelstein coordinates makes a transformation similar to that which was done with the Schwarzschild solution, where you were able to reduce at least one of the sets of singularities into just a coordinate singularity. In other words, you're able to remove it by this transformation. This isn't able to be shown for the r equals 0 and the theta equals pi over 2, and we'll get to that just here in the next slide. The singularity at r equals 0 in the equatorial plane is more complicated, and choosing the coordinate system that you want to work in is important. Some of them, like Cartesian coordinates for the Kerr solution, are very difficult, and computers don't like them very much. So this is from a Mathematica notebook that the professor gave, and here you're able to solve for the quadratic curvature invariant, the Riemann squared term, and the Ricci scalar and Ricci tensor are 0 throughout when you solve them, but the quadratic curvature invariant is not. And if it has a curvature singularity, then it will diverge. It will go to infinity at that singularity. And because it's an invariant, that means that regardless of the coordinate system that you're using, that it will be a curvature singularity in any coordinate system that you use. So you can see here this bottom term right here. This is all multiplied. It's a really long equation. But this bottom term here goes to 0 for the terms of r being 0 and theta as pi over 2, as expected. So it is a curvature singularity, a real singularity, just like in the Schwarzschild solution of r equals 0. The r plus or minus, if you go back, you will notice that as alpha goes to 0, this just becomes r plus or minus equals the Schwarzschild radius. So it reduces to just the horizon for the Schwarzschild metric. The singularity at R, R plus, I won't be talking about the R minus surface, an inner horizon. It isn't really treated in the Hartle book, and there's other things to talk about. But the R plus...
R minus goes to R equals 0, right? R minus goes to R equals 0 in the Schwarzschild limit.
Yeah.
Right. Okay.
Yeah.
So that's what Riemann squared is actually singular, isn't it? Still.
Maybe. Probably. You're probably very correct. Yeah, I'll look at that. So going through this, we're going to be bringing up one additional thing, a null vector. Like the killing vector, didn't discuss it in class, but a null vector is just, or null surface is a 3 surface. In other words, removing one of the coordinates such that you have a 0 line element everywhere. In other words, your ds squared is equal to 0. In doing this, you have just a dot product of 3 different spatial component or space and time components. And when you do the dot product, you have to bring in the metric component here. And this is just some arbitrary vector which we haven't solved for yet. And we're going to, by setting equal to 0, assume that there is a null surface at R plus at the horizon. This, when we reduce it, allows us to get the following equation below. And solving it, we can see that that the L theta term must be equal to 0. And of course, you can see the first 0 here is the LR. We're assuming a constant radius, so that doesn't come into the null surface at all. But then we get this a 1 for the LT term and a term for L phi, which indicates the rotation of the black hole. In other words, the best way to probably think about it is if you were to have photons at that surface, they would rotate with that angular velocity. All right. There are limitations on the Kerr parameter, specifically that it must be greater than 0. You can choose a coordinate system such that it is always non-negative just by choosing it to go one direction. It doesn't actually matter in this case because you square it. But what you do get is that that alpha must be greater than 0 but less than or equal to 1. When it gets to close to 1, they're called extreme rotators or extreme Kerr black holes. And theoretical limits say that it probably gets to about 0.998 gm squared for the rotational, the angular momentum of the black hole. In the equatorial plane, yeah.
Where does this 0.998 come from?
They quote it in Hartle. Models of accretion disks say that it shouldn't get much more than that. They don't explain it necessarily.
So this is theory, though, not observation.
Fair question. They do have some observation to back it up, but I think he was saying specifically theory at that point. But I don't know I haven't looked up the sources. Yes?
Doesn't it have to be theoretical if it's right around the dead horizon? I mean, have we ever measured anything that's going on there? I think no.
Well, I was asking about the specific value of 0.988 or whatever it was. Why that particular number?
Well, it has to do with like stability of the accretion disk. So it's not a relativity limit. It's more like mechanical limit.
Okay. Using again the conserved quantities E and L from before, the energy per mass and angular momentum per mass, and this L is different from the angular momentum J of the black hole, just to not be confused. And L, sadly, just as is typical, L is also used for the null surface L, so don't get confused by that. But when we write out E equals the psi times the 4 velocity u, you get the metric included here, and when you solve this noticing that this is just d phi d tau, you're able to solve this for two equations, one in t and one in phi. The additional things, as you are in the equatorial plane, you can say that there's no forward velocity component in the theta direction, and that with c equals 1, that your forward velocity squared is going to be equal to -1. With all these constraints together, you're able to determine what the r component is, how r changes with proper time. This here, of course, is just related to the energy of the object that's about the black hole. Oftentimes, we just treat that being equal to 0. In other words, it has 0 kinetic energy at infinite r. And in that case, E would just be equal to 1, which is how we did it in class for the Schwarzschild. So when we work through we get an effective potential as such, which is slightly more complicated, but not too much than the Schwarzschild one, which is given below. It is a little more difficult to be able to interpret this, and so you have to hold constant sum or solve for all of the parameters all at once. It's a bit of a pain. And just kind of a reference, there is a limit to the angular momentum of a particle and whether or not it'll be able to fall into the black hole. Continuing the orbits, the effective potential is plotted in the vertical axis, and here we have E equals 1, so we're assuming 0 kinetic energy at infinity, and we are looking at various values of L and alpha. Right here, this is a constant L and constant alpha, and then we are letting alpha and L vary oppositely. We see that you will have a peak for some of them, and some of them will not have any peak, indicating that a particle from infinity will fall into the horizon, into the singularity. But some of them will come in, bounce back, and have an orbit. There is a limit to what orbit you are able to have. There are 3 equations that you can solve, specifically the effective potential equation, and then the derivative of that, which for a circular orbit will be 0. And then if you want a stable orbit, then that means that the second derivative of the effective potential has to be 0 as well. Otherwise, a small perturbation would cause it to fall in or away from the singularity. So solving all these at the same time, you get a set of points. This is, of course, the innermost stable circular orbit versus the alpha parameter of the black hole, and you see that right here, this would be the Schwarzschild radius. You're able to get, for a co-rotating, in other words, so the black hole's rotating in the same direction as the particle about it, you're able to get at about half of the Schwarzschild radius to it, whereas if you rotate in the opposite direction, you will actually not be able to get as close. This is an evidence of frame dragging, and there are actually some really cool pictures where you have a counter-rotating object coming in and all of a sudden reversing its direction and falling into the singularity, just due to the effect of frame dragging in the close limit.
So the dots are just what you used to plot that curve. Those are your dots, right?
Yeah. I just had to solve the equation. I didn't want to.
Because it's a cubic or something.
Yeah, it's a nasty equation you have to do numerically. So, lastly, wanted to talk about the ergosphere. For the Schwarzschild solution, you're able to, if you had enough propulsion, to remain stationary at any point above the event horizon. However, that is not the case with a Kerr solution, particularly if you try to have a constant spatial component of your forward velocity. Then taking the magnitude of that, you're able to get a limit as to how close you can get. In other words, this term right here can't be 0. When you solve that, you're able to find what's called the ergosphere radius, which is related to alpha and, of course, theta. And that this shows that there's a limit to how close you can get without having any type of motion. So any closer than that, and you will fall into the event horizon. It is possible, and I didn't want to bring it up, it is possible to rotate with a black hole and get closer than that within the ergosphere. Just a brief thing towards here the end. This is just a slice of the event horizon R+ here and the ergosphere for an extreme black hole, just to emphasize the difference between them. So you're able to see that that you're able, not even to be, what would that be? That would be a Schwarzschild radius, yeah. So within a Schwarzschild radius in the equator, you're not able to get any closer without falling in or having to rotate. There are a lot of other interesting things. Highly recommend you look it up. The Penrose process, where you're able to get energy out of the Kerr solution black hole, but don't have time for that right now. So thank you. Questions?
How do you interpret this event horizon here? How do you interpret this event horizon here?
The event horizon would be a point at which, if you were within, you would have, space-like separation outside. You couldn't, the forward light cone would go towards the origin there.
I see.
It's just like the Schwarzschild.
Okay, but things can still escape from that, right?
From the outer one, the ergosphere.
Yeah.
Yeah. But the event horizon R+, no.
Okay.
Yeah. The Penrose process is where you shoot in a particle that decays. One half goes into the event horizon R+, and one half leaves with more energy than it started with. So, all right.
Questions?
Yeah.
There is a coordinate in which Kerr solution only have curvatures similarity.
What?
There is a coordinate in which
There's a coordinate system in which the Kerr solution
Yeah.
only has a...
Yeah, the Eddington-Finkelstein. Yeah. I didn't want to put in the full metric for it or anything, but...
Okay. Hi, I'm Anna. I'll be talking about gravitational lensing today. Okay, so you all probably already know this, but just in a nutshell, gravitational lensing is when you've got two objects along your line of sight that are, and the lens object is in the middle. So it has to be pretty massive to actually curve space-time enough for you to observe the lensing effect. So usually we talk about lensing by galaxies. So you have some object that's behind your lens object. The light paths get bent, and then what we see is this asymptote here. So when we trace that back, we see a false image off to the side, and we can see multiple false images. Here's an actual picture of what a lens system looks like. So I'm not going to go through this a whole lot because we derived this in class. Oh, great. Okay, my PDF is missing some of the symbols. But anyways, if you start with the Schwarzschild metric and the free fall equation, and then just assume regular GR, so you don't have to put any of the Brand-Sticky parameters. So here's the Schwarzschild metric. Here's the free fall equation. Then you get the B of R in the metric is 1 minus 2 mg over R. And A of R is approximately 1 plus 2 mg over R when you expand it. So in this diagram, you can solve for the R equation and then make some substitutions so that you have it in terms of dr d phi instead of dr d tau, and then integrate. And that will give you the total deflection angle, which this should say it's 4 mg over EC squared plus higher order terms. And this is actually twice the Newtonian prediction. Okay, so remember that result. This is just the geometry of a simplified lens system that we're going to look at. So this is the observer, U. L is the lens. This S is the source. And then S1 is where you think the source is when you make your observation. The assumptions that we make for the following slides are that these projected distances along our line of sight are very large, so you can make small angle approximations. And also, since these distances are so large, you can also make the thin lens approximation, which is that all of the deflection action occurs in the lens plane. So instead of having a curve like the previous slide, instead of having this curved path, you're just going to replace that with the two asymptotes. And because we're making the thin lens approximation, we can also generalize a 3D lens mass distribution to a 2D distribution that lies completely in the lens plane. So this is just basic geometry, more math that an undergraduate can do. So just labels alpha tilde is the quote-unquote true deflection angle from the first slide that I showed. Plane alpha is the observed or scaled deflection angle. That is the angle between the actual source position and where you observe this image S1. And the lens equation relates the position of your source with relation to the lens to the deflection that you observe. So beta equals theta minus alpha is just from this diagram, and then you can just fill in also alpha is equal to the distance between the lens and the source over the distance of the source times alpha tilde. And that's just from the small angle approximation. Okay, so insert that into the lens equation. So now we have this. And you can solve for the special case where beta equals 0. So remember, beta is the angle between your source object and the lens. So if beta equals 0, that means that your source is directly behind the lens. So you get this theta Einstein, the Einstein radius they call it, is sort of the angular scale that's characteristic for these kinds of lensing events. And of course, if it's directly behind the lens, then there's no preferred direction for the light to be bent into. So you should see just a perfect ring, and you call that an Einstein ring. And these are just some nice examples of Einstein rings from the Hubble Space Telescope. And also, if you plug in numbers, the Einstein radius is about 1 arcsecond for galaxy scales, and that's something that we can observe, obviously. If you're looking at a smaller scale, like a couple stars in our own galaxy, then this is not observable. But you can see some lensing effects. I'll get to that later. So also, if you don't make the assumption that beta equals 0, you can introduce some scaled variables. So x is just a scaled version of theta, and y is a scaled version of beta. And your lens equation becomes something like y equals x minus 1 over x. Can solve that, and you'll get two solutions for x. So what this means is that if you're generalizing to point sources, then when your source is offset from the lens, then you'll get two image positions. And these are some examples. So here are two images. Here's two images. Some of these you'll see multiple images, and that's because if it's not perfectly point sources. Your lens galaxy can have some sort of weird shape, and that will give you multiple image points. Okay. So if you don't just have point sources, obviously lens galaxies are non-trivial two-dimensional mass distributions. So just replace beta and alpha and theta with vectors, and you can define a critical surface mass density. Sigma critical. And using that, you can write a dimensionless surface density that describes your lens. We'll call that kappa. So if you want to find out what is your observed deflection angle given some lens distribution, just do the integral over kappa, this here. And you'll notice that this can be written, you can write alpha of theta as the gradient of some scalar potential, where the scalar psi is given by this expression here. So you should notice that these equations look really similar to Newtonian equations for gravitation. So we have a source term, so kappa is sort of like our source term. We have some scalar potential, and we have some quantity that is the gradient of that scalar. So in gravity, the thing that's the minus gradient of your scalar is the force. So you can think about it as if you have some gradient in your force, you get tidal distortions in your object. So you can take a sphere, and tidal forces will stretch that into an ellipsoid. And the same thing can happen with light being bent by a deflection potential. So a gradient in your in alpha, a gradient in your deflection angle leads to a deformation of your light, of your source image, sorry. So that's what I've shown here. So if you start with a perfect circle and it gets deformed by a gradient in alpha, then it can turn into a rotated, stretched out ellipse. And the way to go back and forth between these two images is the Jacobian matrix. A is d beta d theta, and this is what you get if you do out the math, where kappa is what we were talking about before. And the kappa term will determine the magnification of the image you're seeing. And the gamma 1 and gamma 2 are the parts of your complex shear. So if you write your complex shear like this, where it's equal to gamma 1 plus I gamma 2, then you can also rewrite it with some phase. And this phase determines how rotated this ellipse becomes. The eigenvalues of your Jacobian matrix will give you the major and minor axes. So basically, the gammas tell you how stretched out your ellipse becomes, and the determinant gives you the magnification. And one thing to note is that the surface brightness of your source image is preserved during this transformation. But if you magnify it, then of course you've got a bigger object with the same surface brightness, so the total flux that you receive from your image increases. Okay. So we're going to move on to some applications and different types of gravitational lensing. The first one, and the one that most people think about when they talk about gravitational lensing, is strong lensing. So all those pictures that I showed earlier are examples of strong lensing, where your source actually forms multiple images. And you'll get strong lensing if the determinant of your Jacobian equals 0. So remember before I said that magnification is 1 over your determinant. So yes, that does mean that you can get magnifications going to infinity formally. But that's not that weird, right? Because when you're teaching, like, say, the 3C class here, you can also have your magnification for 1 over d image minus the focal length in a very simple lens system also go to infinity. In practice, of course, you don't really see this because we made some assumptions here, and geometric optics will break down eventually. So this is true if the surface density somewhere in your lens object exceeds the critical surface density sigma. And if you make the calculations for a typical strong lens, critical surface density is about 1 gram per centimeter cubed. Oh, squared, because it's a surface density. Which you can definitely achieve this critical density in galaxy clusters and galaxies. So what can we do with strong lensing? So with gravitational lensing, it's interesting because usually when you think about the use of a lens, you're studying the source object. But the majority of the time, we're actually interested in using gravitational lensing to study the lens object. So we can use it to measure the mass profile of our lens, basically. You can do some math going backwards. If you know what your image is, then what shape does the lens have to be to deform the image into that shape? And one result from this is that if you're looking at the largest scales of dark matter substructures, so galaxy clusters, using gravitational strong lensing, people have found that we really don't know whether a Navarro-Frank-White profile or an isothermal profile is the best fit to the dark matter. So I guess that's not a result. That's like a non-result. So this is one exception to that, where this is actually from the work of Jay Canac here, who's going to defend his thesis next week. And he actually uses strong gravitational lensing to study the faint source object. So in this case, he's interested in studying these faint star-forming galaxies. So these green contours are the actual sources. And then I think this is the interesting column. The blue ellipse is the model that you can get for the source that produces these images.
I was going to say, sometimes the lens, you can't see it, right? Sometimes the
Right.
lens is some sort of black hole.
Right.
In that case, of course, the density would be very high, this density grams per centimeter square that you have.
Mhm.
These are, in this case, though, the lens is visible, is it?
Yeah, so these are galaxy lens systems. So you can see this is the actual image, and then to go from here to here, he had to subtract out the lens object because he was more interested in the source. Another type of lensing is weak lensing, which is a more subtle effect. So weak lensing is if you're a little farther away, or if you don't meet the requirements for strong lensing, you can still see the effect because, like I said, the effect of gravitational lensing is to elongate your image and then rotate it so that it's it's sort of tangent to your source. So this is a picture from Wikipedia of what you should see. So these are unlensed, just more round galaxies, and then if you add in a lens, they'll become stretched out and sort of aligned to form kind of circle shapes around your lens object. And this is an example of that in practice. So the most obvious examples are like here. You can see some stuff has been distorted along an arc, and here.
So with multiple sources in this case, right, with multiple lensing objects.
Yeah, you need multiple objects to do weak lensing. So really, they wouldn't just use these obvious objects. They would use the whole field and do some sort of statistical analysis to come up with the mass distribution for the lens. Yeah, so like I said, you can do the same kind of things that you do with strong lensing, study the mass distribution of your lens object. This is a famous example of how weak lensing was used to measure a mass distribution. So the bullet cluster is sort of it's the example everyone pulls up to say why to support dark matter being a particle instead of MOND. So in this picture, the dark dots are the X-ray emission. So that's all the visible luminous matter in the form of gas. And these are two clusters that came together and impacted. So you can see all the gas kind of stuck together in the middle. But if you use weak lensing to see where the bulk of the mass really is, it's actually offset from the visible matter. So what people say is that these came together, the gas got stuck in the middle, but the dark matter, which was non-interacting, passed through each other. And that's why these came out on the other side. Another use for weak lensing is to measure the cosmic shear. So if you just take a lot of weak lensing measurements all over the place, we know there's dark matter substructure in the universe. If you believe in dark matter, you believe that there's dark matter substructure, and that will lens all the galaxies, and you can come do a big statistical analysis and determine the level of the fluctuations in density. And then the last example of gravitational lensing is microlensing. So for the larger scale types like weak lensing and strong lensing, the distances are sufficiently far enough that you're not going to notice any change in your image. Because even if the lens is passing in front of the source, it's happening on a very, very long, unobservable timescale. Microlensing deals with systems that are closer together. So the timescales are short enough that we will see some change in the image. But because these systems are pretty close, you can't resolve the Einstein radius, or the Einstein radius is very small. So the thing that we actually observe is the change in magnification or the change in brightness of the image. So here's an example of a light curve. So you've got some object passing between you and a nearby star. And then this axis is in days. So over the course of like 300 to about a year, this object spiked in brightness and then went back down after that lens passed through the line of sight. Like Craig mentioned, one notable application of microlensing was to rule out massive compact halo objects as the dark matter candidate. So So there was actually a big survey to look for microlensing events, and when they saw that there weren't enough of these events for the number of machos that you would need to explain away dark matter, machos were pretty much ruled out. A really interesting way to use microlensing is to look for exoplanets. So if you have a star with a planet going around it, if that star is the lens that passes between you and another star that's further away, then you'll get this, this overall big change in brightness. But if you also have a little planet accompanying that star, it's sort of like a perturbation, and that planet produces this additional little spike in brightness. So there are big collaborations that will monitor microlensing events to look for exoplanets. And it's nice because it's especially sensitive to low mass planets, which a lot of other planet finding techniques are not. Oh. And I think that's the end of the slideshow. So any questions?
Is the wavelength affected by gravitational lensing? It looked like from the photo, it looked more blue.
No, so it should be wavelength independent. Yeah, so one way I think that they found out the first strongly lensed quasar, the way they knew it was gravitational lensing was that the two images had the same spectrum and the same brightness and the same color.
You mostly talked about two-dimensional lenses. What about the three-dimensional case? Have you seen anything that is done? I mean, I would imagine it would be just as doable. Look at the lens itself as opposed to being two-dimensional, which is, I think, all you discussed, right?
Mm-hmm. I think in practice, it's mostly all two-dimensional because
you can use simple formulas and things.
Yeah, and I mean the sizes of those objects are so small compared to the distances between them that it's good enough to use the projected mass distribution. I think the other errors that you would get from these kinds of observations would be a lot bigger than the errors from that.
Yeah. Okay, so hi, I'm Chris. I'll be talking to you guys today about gravitational wave detection, generation and detection. Before we get started, it's sort of trying to condense a lot of a broad field into a very short talk, so I'm going to probably breeze through a lot of stuff really quickly. This is not my field of expertise, so feel free to chime in at anything that I've overlooked or misrepresented. But anyway, let's get started. Here's a quick overview of what I'm going to talk about. Just talking about direct detection versus indirect detection and different cosmological sources for gravitational waves. But before we get started with that, just a real quick recap about gravitational waves. I find it useful to have kind of an intuitive definition of what these things actually are. I like to think of them as tidal forces which propagate as waves. And the speed at which they propagate is the speed of light. And as we showed in class, there are two non-trivial polarization states, which we call the cross polarization and X polarization. You can see that by rotating one 45 degrees, you get the other. And as the professor pointed out in class, this is consistent with the idea of the graviton being spin 2. So here are just two animations that show the two different polarizations. The points on those animations would represent test particles, the way that they would be affected by gravitational waves. And then the diagram in the middle just shows some tidal force lines as well. So you can see that for both of these, what you essentially have is space being squished in one direction while being elongated in the other direction. And that's going to be the important characteristic of these waves that we measure. And we're going to call the amplitude of a gravitational wave basically the amount of stretching or the distance change between two of those particles relative to the initial displacement. And of course, these are extremely exaggerated. In reality, we're looking to detect things where that amplitude is on the order of 10 to the minus 21 or even lower. Okay. And then just real quick here, gravitational waves are inherently a quadrupole phenomenon. There's no such thing as monopole radiation. So spherically symmetric distributions, just shrinking and expanding, won't give you waves. And as far as we know, there's no such thing as negative mass. So mass dipoles aren't something that we need to consider. So it's apparent that that quadrupole radiation is the lowest contribution. And then just real quick, this basically gives you the luminosity from a time-changing quadrupole moment. You can see it's related to the third time derivative. And then the simplest quadrupole you can think of as a dumbbell, basically two masses separated by a certain distance. And if those masses are rotating about one another, you'll have a change in the quadrupole moment, and you'll have gravitational radiation. So here's a diagram and a couple equations, basically for this specific scenario, talking about the luminosity. And then by taking a sort of quasi-static point of view, you can derive expressions for how the radius and the angular frequency of the orbits change with time. And this was just taken from the textbook I used back at RPI. We didn't use Weinberg because Ohanian was an emeritus professor there, so we used his book instead. But anyway, so moving on, just to talk a little bit about direct detection methods. So the early attempts at making gravitational wave detectors, again, recapping what we talked about in class. Gravitational waves are inherently a quadrupole phenomenon, so you would expect them to couple to mass quadrupoles. So one way of possibly detecting these things is to make a big-ish mass quadrupole, like a big cylinder of metal, and then measure how that cylinder absorbs energy from gravitational waves. So these things can be reasonably sensitive on the order of the sensitivity of the first generation of ground-based laser interferometers, but they're only effective over a very narrow range of frequencies. You basically need to be right on the mechanical resonance frequency of the detector in order to have any sort of measurable effect. And this is just a picture of this picture that shows up in every talk about this, so I figured I'd include it here, of Joe Weber working on one of the early bar detectors. And then the other main type of direct detector is the interferometer. Basically, the diagram here is it's just a big Michelson interferometer. You have two bars two arms at right angles, and you try to measure a phase difference between light propagating in each of those arms. You suspend large mirrors at each end. They act like the free masses, so they behave like you would expect those test masses in the if we go back. So they essentially behave like these test masses here. So one end of the interferometer is going to shrink, and the other is going to expand, and that's going to generate a phase difference that you can measure. Essentially, the travel time for the wave going down one arm of the interferometer will be lessened, and the other will be increased. And it's analogous. Since the wavelength of the gravitational radiation is much longer than the typical characteristic size of these interferometers, it's helpful to think of them as antennas. Basically, they operate in the same regime, which makes it useful to think about the antenna response of an interferometer. The sensitivity to measurements of different polarizations is going to depend on where that gravitational ray is coming from. So here's just a couple of those plots. Here, the center of the interferometer is at the center of the diagram, and then the two black bars represent the arms. And here, this surface, the distance from the center is essentially the sensitivity in that direction. And then for the two linear polarization states, and then for unpolarized, just so you can get a sense of that. Okay, so we can talk specifically. The two most competitive experiments currently characterized as ground-based interferometers are LIGO and Virgo. LIGO is a set of three interferometers, one of which is smaller than the other two. The two big ones both have 4-kilometer arm lengths. And even though the physical size of the arm is 4 kilometers, they basically create a resonance, a cavity that allows multiple reflections back and forth. So the effective arm length with respect to the detection efficiency is considered to be on the order of hundreds of kilometers. And then LIGO, the first, I guess the initial LIGO experiment, I'll talk a little bit about advanced LIGO and advanced Virgo in a minute. But LIGO initially had the better peak sensitivity as opposed to Virgo, which is one detector located in Italy, slightly shorter arm length, not as good of a peak sensitivity, but they invested significantly in the isolation mechanism for their mirrors, which gives them much better damping against seismic activity. So they actually have a much better sensitivity in the low frequency range, below 40 hertz. And to just characterize that, what we're looking at here is basically a graph of sensitivity as a function of frequency for the initial LIGO and Virgo detectors and the planned advanced LIGO and advanced Virgo deployments, which both these detectors are currently being retrofitted. So you can see here the red curve is LIGO, and you can see that. So basically, what we're looking at here is a noise spectrum. So essentially, at a given frequency, your signal would have to be higher than the noise in order for you to detect it. That's the way to interpret this diagram. So we can see what I was talking about before. LIGO has a lower noise, the lowest peak noise, which means it has a better peak sensitivity. But it blows up above around 40 hertz, whereas Virgo was much more sensitive down to around 10 hertz. And the advanced LIGO and advanced Virgo retrofits, you can see that they're an order of magnitude more sensitive. So they should be able to detect much more real physics events. So what's usually quoted for LIGO and Virgo is that their sensitivity is to an amplitude of about 10 to the minus 21, whereas the advanced ones minus 10 to the minus 22, 10 to the minus 23. And again, remember, that's just change in length over length. So it's a unitless measurement of the strain from a gravitational wave. And then possible future detectors. We're looking to hopefully build an interferometer in space. That project is called LISA, which has been in sort of a dance trying to get funding from NASA or the European Space Agency. But it would have an arm length of about 10 million meters. And it would be sensitive to much lower frequencies. It would possibly be able to detect sort of stochastic backgrounds from supermassive black hole mergers and things like that. So maybe someday. And here's a little diagram, which is obviously not to scale. And another potential way of directly detecting gravitational waves are these so-called pulsar timing arrays. Basically, you can think of pulsars as natural clocks. Their maximum repeat at a very stable frequency. They have with a certain sort of spin down, which you can calculate. And then by looking at many of these timing signals that are very far away, you can look for residuals in those timing signals to look for extremely low frequency gravitational waves that are affecting the space between Earth and those pulsars. So yeah, frequencies on the order of nanohertz. And again, looking to just detect the stochastic background with those guys. Okay, so yeah, so moving on to indirect detection of gravitational waves, which doesn't sound as exciting, but in reality is where we've been more successful in actually proving that there's a reason to believe that these things exist. So the first real confirmation that gravitational waves are a thing came from Hulse-Taylor's observation of a binary pulsar. They discovered this pulsar and monitored it over many years, and the decrease in the orbital period showed an extremely good match with the predictions from general relativity. So here's a plot from a paper in 2005, which includes some of that data for that pulsar. And that was our, so this is the work that they got their Nobel Prize for in 1993, I believe, which basically very, very strong evidence that rotating or co-rotating bodies at least lose energy due to gravitational processes. And then, if anybody's looking in 300 million years, this pulsar might, these rotating pulsars might merge, and we'll be able to get a signal that would be detectable with our current generation of interferometers. But hopefully we've made some progress by then. Anyway, and then another indirect detection technique is for looking at the different polarization modes of the cosmic microwave background. So this is the BICEP2 result that's been in the news recently. Effectively, basically, B-mode polarization is like the curl of the polarization. You can sort of deconvolve the polarization field into components that are due to the gradient of a scalar field, and then these curl components. And those curl components are the B-mode. And they measured, it's actually easier to see if we go up to the blown up one here. But this is their measurement for the B-modes. And so these lines, you can see how they sort of curl. And this curling mode they measured in with more than the 5 sigma excess of what their background expectation was. So that was their discovery that they have a indirect detection of gravitational waves, through this cosmic microwave background. And such large amplitude primordial gravitational waves are associated with inflationary theories about the early universe. So this is also seen as sort of evidence for inflationary theories as well. Okay, so now a little bit more about how these things are actually generated. So in the wild, gravitational waves that we expect to see with our interferometers are going to be produced by similar objects to these, to what Hulse-Taylor discovered, these co-rotating neutron stars or black holes. So basically, so I'll try to go, I won't dwell too much, but you can see, you can derive expressions in the mode where they're not so close that they're actually merging and you need to do advanced computational calculations, but in the sort of quasi-static approximation, you can derive a frequency and an amplitude as a function of time. And these both blow up as you get closer to the time that they merge, which gives a characteristic chirping signal. Basically, the frequency and the amplitude both go up as these orbiting bodies merge. And that's the signal that we hope to maybe be able to detect with these interferometers. And to just give an idea about whether or not we actually expect to see these things, this table here shows the expected merger rates. NS is neutron star and BH is black hole. So this is for neutron star, black hole. How many of these we expect in a MWEG is a Milky Way equivalent galaxy per million years. So you can see that these things are not very common, and the likelihood of seeing one in our galaxy is very low. But when you look at a collection of more distant galaxies and account for the detecting sensitivities of the LIGO and Virgo interferometers, you can see that we didn't really expect, except on an off chance, to observe them with the initial runs of these experiments. But there is maybe some hope, at least in the moderate regime, that we might be able to see them with the advanced retrofits.
Do you have a graph of this chart?
Oh, an actual waveform? No, I don't have one of those.
That's an interesting form.
Let's see. So the frequency. So you can see the frequency dependence goes like tau to the minus 3/8, and the amplitude dependence goes like tau to the minus 1/4. So yeah, I mean,
The amplitude goes dramatically up.
yeah. So yeah, basically it's just as a cartoon, I guess. I'd have to check the details, but you expect lower frequency.
Right, frequency.
Right. Yeah, that's not very good. but basically something like that, and then
there's a
you.
cutoff.
Well, yeah. Then you get into a regime where tidal forces are very important. You can no longer treat these things as point masses, and you have to do more complicated numerical studies. That's the actual merger phase.
Which has been
So-
done. Which has
Oh
been
yes,
done. So
yes. I don't have those. I don't have any of those results here. I didn't look in depth into that. But this is just to give sort of an idea.
Yeah, no, the point that there is a real characteristic signal. So that's what they will be looking for. They will be
Oh
looking
yes.
this
For these, yeah. I glossed over it here, but yeah, those numerical simulations have been done. There is a we do have a good idea what the characteristic waveform should look like. I don't have the knowledge right now to draw it accurately. But by knowing what we expect to see, it helps with our sensitivities as well. Yeah.
And Chris, where is the cutoff at like when they merge at equal 0?
Yeah, it's the distance when the distance becomes comparable to the size of the objects. So this approximation, you can probably push it down, like for rotating neutron stars, probably push it down to like 20 kilometers or something like that. And then at that point, you need to do the more detailed calculation. Okay, so let's try to. Okay. Another type of another thing that we might excuse me. Another way to produce gravitational waves astronomically is through so-called burst events. These are going to be brief moments of high amplitude gravitational wave generation that we don't have as good of a model for an actual waveform, unlike the co-rotating neutron stars and black holes. So one candidate would be non-uniform supernova collapse. Again, remember, there's no such thing as monopole radiation, so a symmetrical supernova isn't going to give you anything as far as gravitational waves. Although there is some evidence that we should expect there to be an asymmetry in supernova collapses, just from the fact that neutron stars, which we believe to be generated by supernova events, tend to have very high relative velocities compared to their nearby stars, which suggests that there's an asymmetry there. And then yeah, this is another one of those sort of back of the napkin expressions for what the amplitudes we expect from a supernova collapse is, basically relating to the amount of energy that's released. And by putting some marginal values in there, we would expect that if there was a supernova in our galaxy, we would probably be able to detect it with the initial runs of LIGO or Virgo. And then some scenarios for supernova collapse, like bar mode instabilities, where basically a highly rotating star is perturbed in such a way that it collapses into a quickly rotating quadrupole, which is exactly what you want to generate a lot of gravitational radiation. Those modes of collapse could potentially be observable from other galaxies. And then another potential way to get bursts of gravitational waves is these by flares of these so-called magnetars, which are essentially neutron stars that have anomalously high magnetic fields, which are thought to be the physical objects behind soft gamma ray repeaters and anomalous X-ray pulsars. These have been known to occasionally give off extremely luminous flares of radiation, and some models propose that they basically radiate by reorganizing their extremely strong magnetic fields, and some models suggest that the they may release comparable amounts of energy in the form of gravitational radiation, in which case there's maybe some hope that these could be observed as well. And on top of that, there are also some continuous sources. In the context of interferometers, continuous sources basically refers to just quickly rotating neutron stars that have some non-axially symmetric distribution. So again, I won't dwell on the equation here because I think I might be running out of time. But basically, basically that's the equation that gives you the amplitude for a rotating neutron star. And then on top of that, there are also some stochastic sources. We don't expect which basically a background of gravitational waves from things like cosmic string cusps or coalescing supermassive black holes, which would be in the regime of ultra low frequency, which we could perhaps detect with space-based interferometers. And then the primordial gravitational waves from the early expansion of the universe, which is what BICEP 2 believes that it found. And then just generally the summation of all the binary coalescences from faraway galaxies, adding up to basically a stochastic background of gravitational waves. All right, so that's basically it. Just a couple concluding remarks that in gravitational wave astronomy there is, I just wanted to mention that there is some hope of getting some new physics. A detailed look at the waveforms from an actual neutron star coalescence could give us some information about the equation of state for neutron stars, also just provide a deep confirmation of general relativity, and also just as sort of a way into supernovas, since gravitational waves aren't modified as much as light from propagating through dust and other matter. And then we may, if we looking at that plot of the expected rates of observations of neutron star coalescences, there is some hope that with the next generation of ground-based interferometers, we could begin to see some actual physics signals. And then to just highlight, even though we've only achieved indirect measurements of gravitational waves, they can tell us a lot or about our universe and at least confirm what we know from general relativity. So then I have a list of references. I just want to point out, I mostly followed this review by Riles. It's worth reading it if you want to get a little more background here. And that pointed me to most of my other references as well. So I'd recommend that. And then yeah, so I'm all done. So if there are any questions, feel free. Yeah.
I sort of don't understand for the BICEP result, like the two kinds of polarizations. I understand like the transverse and the one that's in the direction of propagation. But when you're talking about the ones that are like the curl versus the divergence, do you have any idea what kind of objects produce more of one than the other? Does it make sense, that question?
Yeah, sort of. It's going to be, again, highlighting that I'm not an expert in the field. But yeah, E-mode polarization is what we expect to be the dominant form. You expect polarizations to be along the lines of temperature gradients in the cosmic microwave background, essentially. And so B-mode is basically your other. That's effects from propagating through gas that introduce a circular polarization that causes you to measure a curl in that polarization field, and things like gravitational waves, which give you the opportunity to sort of misalign those polarization vectors with respect to those gradients. So basically, naturally, we expect the radiation to be sort of this E-mode, right? To be curl-free, but then there's other parameters that sort of give it a curl, right? Any others? Thank you.
Okay, hi. I'm Nick. My presentation is on frame dragging, and in particular the dragging of satellites around the Earth. So a quick outline of my talk. So I'm going to start by talking about this parameterized post-Newtonian formalism. And the reason for that is because in the solar system, generally, we're dealing with a low velocity, low mass limit. And so you don't need to deal with the equations, with Einstein's equations in their exact form. You can use these expansions, and it works out pretty well. And then I'm going to talk about the precession of gyroscopes using this formalism. In particular, there's two effects called the geodetic effect and then the frame dragging effect. And then I'll focus particularly on one experiment, which is called Gravity Probe B. I'll go over the experimental setup, some of the challenges they face, and the results that they came up with. And then finally, I'll just mention a few other experiments that I've tried to measure the frame dragging. So the whole idea behind PPN is that the full solutions are unnecessary and usually difficult to solve. And they're completely unnecessary within the solar system. So what we do is we expand things in terms of small parameters, namely v squared and the potential GM over r. And then we can construct, so the nice thing about this is we can construct a single post-Newtonian theory that it's very general. It can approximate any potential metric theory of gravity that you have by sticking in an arbitrary set of parameters. So one example of these parameters is just this one. So there's 10 parameters. And this is, so for instance, in order to get Einstein gravity out of this one, you just set all of these parameters equal to 1, except for these two. And most of them have some kind of physical intuition that you can associate with them. So once you've set up your parameters, you can write out the various quantities, like the metric, your forward velocity, your stress energy tensor, in terms of them, and then go about solving whatever equations you need to whatever order you need the accuracy for. All right, so precession of a gyroscope. So as long as we can neglect tidal forces, the spin of a gyroscope will obey what's called Fermi-Walker transport, which is just a generalization of parallel transport. And so that equation is given here. So additionally, the easiest way to deal with this equation is to work in a coordinate frame that moves along with the gyroscope. And so I've just sort of written that out here just to be explicit. So coming from this, you do some manipulations, and what you end up with is this term is actually equal to the precession with respect to the co-moving frame. And then you evaluate this term, you do some work to do that. And eventually what you end up getting is, in terms of three-dimensional vector notation, you get this expression where the angular velocity of the spin axis precesses at this rate. So there's a bunch of terms here, and I'll talk about those in the next slide. But basically, this equation describes, again, in complete generality, the precession of a gyroscope spin relative to a co-moving frame that is rotationally tied to the PPN frame, which is fixed relative to all your background stars and galaxies. So again, I just wrote the same expression for the angular velocity here. So there's three terms that appear. This first term is the Thomas precession, which we can neglect for a body falling freely. This last term is caused by the curvature of space-time. And so as you travel through a curved space-time, you'll pick up some rotation. And so if we pretend that the Earth isn't moving, we can ignore both of these terms, and we get just get this part of the angular velocity. And so if we want to get a rough order of magnitude estimation for the effect of this term, we can put in some numbers, right? So this guy is the grad u, and this guy is the velocity. So for a gyroscope in polar orbit around the Earth, you end up with a number that's roughly 8 seconds of arc per year, which is small, but not hopelessly small. So we do have some chance of measuring this. The precession, again, this is what's called the geodetic effect. And that is not frame dragging, right? So that's something different.
So the gamma is the gamma that for Einstein's theory is
yeah. So this gamma, again, so you'll see these various parameters appear. That those are just the ppn parameters, and so most of the time they're just 1. I think all of the ones that appear are 1, so you can just kind of ignore them. This I was following actually just to give you a reference. I followed Misner, Thorne, and Wheeler for this. So now if the Earth is rotating, and I've been assured that it is, then you get the off-diagonal terms in the metric. Right? So this term in the angular velocity equation, if you work out what those are, you end up getting this expression, where these deltas, again, are just ppn parameters, and they're equal to 1. And so this whole thing right here is just equal to 1. So qualitatively, if we study this, what we see is that near the north and south poles, an object will rotate in the same direction as the Earth. But if you're closer to the equator, you actually rotate in the opposite direction. And sort of an analogy to understand this is if you imagine putting like a spherical ball or something inside of a tank of water or something, and it starts rotating. If you put something near the pole, it'll obviously rotate in the same direction. But if you put it near the equator, what happens is the water closer to the ball is moving faster than water away from it, and so it actually turns the objects the opposite direction. So sort of qualitatively, that's what's happening here. So again, we want to try and get a rough estimate for the magnitude of this effect. So you put in some rough values, and you end up getting 0.1 arc seconds per year, which is about 2 orders of magnitude smaller than the geodetic effect. But still, both of these effects, this is called, the effect due to frame dragging is called the Lense-Thirring effect. And we realized, some people back in 1960 realized that both of these things should be observable, and that we can construct an experiment to try and test general relativity. Right. So that experiment would become what's called gravity probe B. So again, it was supposed to measure the geodetic effect and the Lense-Thirring effect so the geodetic effect 1 part in 10,000 and the Lense-Thirring effect to 1%. The conceptual design for it was actually first proposed back in 1959, and then more work was done started in 1960 at Stanford, and that's what would go on to become the gravity probe B collaboration. So just keep that date in mind when I talk about when it actually finished running. So the gyroscopes were actually listed in the Guinness Book of World Records for being the most perfectly spherical objects ever created. And the reason they needed to be so spherical was because they just wanted to minimize any potential Newtonian torques that would overwhelm the relativistic effects. So they were about the size of ping pong balls, and they differed by no more than 40 atomic layers, which is less than 10 nanometers. So to give you kind of a sense of how spherical these things were, if you blew these up to the size of the Earth, the tallest mountain or the lowest valley would be about 8 feet. So again, another kind of annoying thing was, because the orbit had to be very precise, it had to be exactly over the poles, their launch window was only 1 minute, and so the first launch had to get scrapped because there were some changing winds in the atmosphere. And we got all of this for the low, low cost of $760 million. Right, so the experimental setup for Gravity Probe B, you can kind of see a cartoon of it here. This is the satellite, so it rotates over the poles. And the reason they do this is to separate the two precession effects, the one due to the geodetic effect and the lensiteering effect. So if you have it rotate over the poles, the rotation of the Earth will pull it in one direction, and then the rotation, or the orbit, will pull it in the other direction. And so you have the two effects perpendicular to each other. So these numbers here, the 6.6 arc seconds per year and the 39 milliarc seconds per year, are the predictions from general relativity. And the other thing is that you have to fix your, so the spin will precess relative to the fixed coordinate system, or the fixed stars. And so you align your spacecraft with some star, and you use a guiding telescope to do that. So in the spacecraft, they had 4 London moment gyroscopes. So what a London moment gyroscope is just a gyroscope that has, they coat it with niobium, and then they supercool it, so it's a superconductor. And what happens is, if you have a spinning superconductor, you get a magnetic field which is aligned with the rotational axis. And so that's how and then they can measure the direction of the magnetic field using squids. So that's how they measure the spin. Yeah, these are just some other facts. The gyroscopes had to be stored in vacuum flasks, supercooled to 1.8 Kelvin. And they had to minimize any torques or interactions, so they had to suspend it with electric fields. So they faced a lot of challenges. So here's just a picture of the gyroscopes. So this one is they're made out of fused quartz. So this one, and then they coated them with niobium, which is just a metal. So that's shown there. So again, they had to be really spherical. The squid calibration is always kind of a mess. So measuring the proper motion of the guide star was a challenge. And they also had to deal with helium evaporating and escaping from the vacuum tubes, or the vacuum containers. But they actually came up with a clever way to use this to their advantage. So they had to deal also with atmospheric drag, right? So you want your spacecraft to be in perfect free fall. But even at 642 kilometers in altitude, there's still some atmospheric drag. And so what they did was they had 8 microthrusters on the spacecraft, which would blow little puffs of escaped helium gas out. And these puffs were supposedly orders of magnitude less forceful than a human breath. So that's the kind of precision that they had to correct. That's the kind of corrections that they had to make in order to do this measurement. So the biggest problem that they encountered, which they sort of anticipated, but they didn't correctly anticipate how much it would affect things, were that because the gyroscopes were not perfectly spherical, they got patches of charge, which caused the spin axes to not be perfectly aligned with the moment of inertia axis. And that misalignment caused there to be unwanted torques. And another thing was that, this was, I think, completely unexpected, was that every so often they noticed that the spin would migrate by tens of arc seconds over the course of a day. And the reason for this was because there was some resonance going on between the precession of the gyroscope's axis and the spacecraft, which was rotating in order to cancel out some torques. And so when this rate of precession was like an integer multiple of the spacecraft's roll period, then you got this resonance, and it would cause the spin axes to precess more or much faster. And that was not an anticipated effect. And the real problem was that they'd only realized these things after they'd put the spacecraft up and taken all the data. And so this thing was launched in 2004. And initially, they had expected to have their analysis complete within a year after that. But it actually took them more than 5 years in order to understand the effect of the charge patches. So they created, once they had created a model and applied it, the uncertainties were much larger than they had anticipated. So earlier I said that they had wanted to measure this effect, the geodetic effect, to 1 part in 10,000, and the frame dragging effect to 1%. And you can see what they actually ended up getting was about 0.3% and 19%. But all that considered, they still got results that were completely consistent with theoretical predictions. So here I show you the theoretical prediction, and then here are the experimental results with the error bars. And then in this plot, we just plot the, so this axis is the lens-adhering effect, and this axis is basically the geodetic effect. And gyro 2 was particularly poorly behaved, which is why it has sort of the largest error there. But you can see right in the middle there's the theoretical prediction, and then the joint result from all of these different gyros is right around that.
Gyro 2 just barely makes it, huh?
Yeah. So just a few other experiments which I didn't look into quite as in depth. So there's these Lagios 1 and 2 satellites, and basically they're reflective satellites that are rotating around the Earth, and we track their position very accurately by shooting lasers at them, and then the lasers reflect back, and we can track them that way. And so in principle, the lens-adhering effect should drag the orbital planes of these satellites, and because we know their position so precisely, we can actually measure the lens-adhering effect that way. The problem is we have to assume the correctness of the geodetic effect. So another one is this Mars Global Surveyor, which was launched in 1996 and put in orbit around Mars in 1997. And some people have tried to use data from that in order to constrain this effect. There's been some controversy over how they did that. And then the latest one is this Larry's one, which is very similar, I think, to these satellites. It was launched in 2012. It's supposedly the densest known object orbiting the solar system. And their goal is to measure the lens-adhering effect to an accuracy of 1%. And as I mentioned, there's some debate as to all of these, the procedure and how accurate they can do it. But supposedly, so the kind of terrible thing is that this, if this is correct, they'd done this even before Gravity Probe B launched, and so they ended up doing better, even though, and so they spent all this money trying to measure this thing, and then it wasn't even the best measurement to date. But yeah, I think it was interesting. So that's all I have. Are there any questions?
What is this business of the densest known object orbiting the solar system?
Yeah, that's just sort of, I just read that on their experiment page. I guess they like to brag about, like how Gravity Probe B like to brag about their.
Do you remember what
I don't remember. But yeah.
Is it big? Is it small? I can't remember.
Yeah.
Any other questions?